Imagine a control panel with dozens of dials on it. Each dial is set to an extraordinarily precise number. Nudge almost any single one of them, even by a hair, and every star in the sky winks out. Every atom falls apart, and life anywhere in the cosmos becomes impossible. That's not science fiction. That's a description physicists actually use for the universe we live in. Last time, we talked about how the universe began. Today we're going deeper into the actual numbers baked into nature itself, and why so many scientists, including atheist ones, call this the fine-tuning problem. Physics runs on a small set of fundamental constants, numbers that aren't derived from any deeper theory. They're just measured. Things like the strength of gravity, the strength of the strong and weak nuclear forces, the mass of the electron, the cosmological constant that governs the expansion of space. Nothing in the equations of physics requires these numbers to be what they are. As far as we can tell, they could have been almost anything. And yet, when scientists calculate what would happen if these values were even slightly different, the results are staggering. Not life would be a bit harder. Not evolution would look different. Total, catastrophic failure. No stars, no chemistry, no atoms heavier than hydrogen. In many cases, no universe capable of lasting longer than a fraction of a second. Physicist Paul Davies, no friend of traditional religion, has written that the impression of design in cosmology is overwhelming. Sir Fred Hoyle, an atheist astronomer, said flatly that a common-sense interpretation of the facts suggests a superintellect has monkeyed with physics. Let's look at some of the actual dials. The strong nuclear force holds protons and neutrons together in the nucleus of every atom. It has to overcome the electromagnetic repulsion between positively charged protons, which desperately want to fly apart. If the strong force were just a few percent weaker, deuterium, an early building block needed for nuclear fusion, wouldn't hold together. Stars couldn't fuse hydrogen into helium. No stellar furnaces, no heavier elements, no carbon, no oxygen, none of the chemistry life depends on. If it were just a few percent stronger, hydrogen would fuse too easily and too early. Stars would burn through their fuel almost instantly, and the universe would likely be filled with heavy elements and almost no hydrogen. No long-lived stable stars like our sun to warm a planet for billions of years. There's an even more specific example here. The element carbon, the backbone of all known biochemistry, only forms in stellar cores because of a very particular nuclear resonance, an exact energy level inside the carbon-12 nucleus. Fred Hoyle predicted this resonance had to exist, purely because he knew carbon existed in the universe and worked backward. When it was found exactly where he calculated, it stunned him. Famously enough, that this coincidence is part of what pushed him towards suspecting design in nature. Gravity is by far the weakest of the four fundamental forces, and that's exactly why we're here. Physicists describe gravity's strength relative to the other forces using a number so small, it's hard to picture. Compared to electromagnetism, gravity is weaker by a factor of roughly 10 to the 36th power, a 1 followed by 36 zeros. Here's why that precise weakness matters. Gravity is what pulls matter together to form stars and planets. If gravity were only slightly stronger, stars would form from less material, burn hotter, and collapse faster. Many astrophysicists estimate stellar lifespans measured in millions of years rather than billions. That's nowhere near enough time for life to arise and evolve on an orbiting planet. If gravity were slightly weaker, matter might never have clumped together at all. No stars, no galaxies, no planets. Just a thin, cold haze of gas drifting apart forever. The margin physicists describe for a life-permitting strength of gravity, relative to its total possible range, is often described as staggeringly narrow. Some estimates put the tolerance at around 1 part, in 10 to the 60th power. This might be the most jaw-dropping example of all. The cosmological constant governs the energy density of empty space itself. It's what drives the expansion of the universe. Physicist and Nobel laureate Steven Weinberg calculated the degree of fine-tuning required here, and the number is almost impossible to say out loud with a straight face. Physicists often describe the required precision at somewhere around 1 part in 10 to the 120th power. To put that in perspective, that's a more precise calibration than hitting a single specific atom if you were to lay a ruler across the entire observable universe. If this constant were even slightly larger, the universe would have expanded so violently and so fast that matter could never have clumped into stars or galaxies at all. If it were slightly smaller, or negative, the universe would have collapsed back in on itself within a fraction of a second, before atoms could even form. Roger Penrose, another Nobel-winning physicist, calculated the improbability of the universe's extraordinarily low entropy starting conditions and arrived at a number so large, 1 in 10 to the power of 10 to the 123rd, that it doesn't meaningfully correspond to anything we can picture. He said, finding a number like that written out in full wouldn't even be physically possible, since you'd run out of room to write all the zeros, even if every particle in the universe were a zero. So, scientists agree on the data. The disagreement is over what explains it. Broadly, there are 3 responses on the table. 1. It's just a brute fact. The universe is this way because it's this way. Full stop. No explanation needed or possible. Many find this deeply unsatisfying. It treats staggering precision as something to shrug at rather than something to explain. 2. The multiverse. If there are an enormous, perhaps infinite, number of other universes, each with different randomly generated constants, then it's no surprise we find ourselves in the rare one that supports life, because we couldn't exist to observe the others. This is a serious position held by respected physicists, but it's worth noting there is currently no direct observational evidence for any other universe, and some critics argue it simply relocates the mystery, trading one unexplained fine-tuning for an unexplained universe-generating mechanism. 3. Design. A single universe, deliberately calibrated by an intelligent cause for the purpose of supporting life. I won't pretend the third option is the only one a reasonable scientist can hold. Brilliant physicists land in all 3 camps, and this deserves honest engagement, not a dismissal of the alternatives. But when you stack up the sheer number of independent constants that all had to land in an extraordinarily narrow range, together with the fact we already have good philosophical reason, from the universe's very beginning, to believe a powerful, intentional cause exists behind it all. Design stops looking like the religious answer smuggled into science. It starts looking like the answer that best fits the evidence. The palmist wrote, "The heavens declare the glory of God. The skies proclaim the work of his hands." He didn't know about the strong nuclear force or the cosmological constant, but 3,000 years later, the numbers themselves seem to be saying the same thing. A universe that didn't have to permit life, calibrated with a precision that borders on the incomprehensible, so that life, including you, watching this right now, could exist. That's not proof you can hold in your hand, but it's a universe that looks a lot less like an accident, and a lot more like a home, prepared in advance for the people who'd one day live in it. If this helped you see the universe a little differently, subscribe, and I'll see you next time, where we'll look at the origin of biological information and why even simple life may be pointing the same direction.